Hello and welcome to another GCSE revision video, and in this video we're going to be looking at the unit circle. SOHCAHTOA works very well for right angled triangles where the angle is between 0 and 90 degrees, but there are such things as obtuse angle triangles where the angle is greater than 90 degrees, so somehow we need to come up with a definition of sine, cosine and tangent that works for angles that are bigger than 90 degrees. Let's begin by constructing a circle of radius 1 unit centered on the origin. The x and y axes divide the circle into 4 quadrants. We can construct a right-angled triangle from the xy coordinates of the radius simply by dropping a perpendicular down from where the radius touches the circumference to the x-axis. And this creates a right-angled triangle where the hypotenuse is 1 unit. We can now use our SOHCAHTOA definitions to say that, at least for the first quadrant, x is equal to 1 times the cosine of theta and y is equal to 1 times the sine of theta. But we know that 1 times anything is itself, so x would be the cosine of theta and y would be the sine of theta. So why not extend this definition to work all around the circle? So the cosine of theta is the x-coordinate and the sine of theta is the y-coordinate of the point where the radius meets the circumference of a unit circle. And we'll remember that a unit circle is just a circle of radius 1 unit. That unit can be a millimetre, a kilometre, a light year, an angstrom unit, it could be a mile, it could be an inch, it could be the length of your fingernail, it could be anything. And since the y-coordinate is the same in both quadrant 1 and quadrant 2 of the unit circle, it's very easy to visually see why sine theta is equal to sine 180 degrees minus theta. We can also observe that the distance along the x-axis is the same but in the opposite direction. So the cosine of theta is equal to the negative cosine of 180 degrees minus theta. There are other values for cosine and sine that become apparent when we think of sine and cosine in this way. For instance, the points where the radius crosses the x and y axis. So we can easily see that the cosine of 0 degrees is 1 and the sine of 0 degrees is 0. Likewise, the cosine of 90 degrees is 0 and the sine of 90 degrees is 1. Again, the cosine of 180 degrees is negative 1 and the sine of 180 degrees is 0. And the cosine of 270 degrees is 0 and the sine of 270 degrees is negative 1. And the cosine of 360 degrees is the same as the cosine of 0 degrees, which is 1, and the sine of 360 degrees is the same as the sine of 0 degrees, which is 0. There are also a number of special angles you will need to know for your GCSEs. If we consider an equilateral triangle, we know that all 3 angles are 60 degrees. So let's draw an equilateral triangle where all 3 lengths are 1 unit. If we split the equilateral triangle straight down the middle with a perpendicular bisector that cuts the vertex in half, then we have 2 identical right-angled triangles. Now the length that is opposite the 30-degree angle is the hypotenuse multiplied by the sine of 30 degrees. But the hypotenuse is 1, and anything times 1 is itself. So the length opposite the 30-degree angle is just the sine of 30 degrees. But the length opposite is 1/2 a unit, because the triangle was equilateral where all lengths were 1 unit and the length was cut in half. So the sine of 30 degrees is 1/2, or 0.5. But the same length that is opposite the 30-degree angle is adjacent to the 60-degree angle, which means the cosine of 60 degrees is 1/2. We can use Pythagoras' theorem to get the length of the perpendicular bisector, which is also the height of the triangle. So the height squared is equal to 1 squared minus 1/2 squared. So that means the height squared is equal to 1 minus 1/4, because 1 squared is 1 and 1/2 squared, or 1/2 times 1/2, is 1/4. That means the height squared is equal to 3/4. Since we're talking lengths and there's no negative lengths, we're only looking at the positive square root of 3/4. So the height is the square root of 3/4. And the square root of 3/4 is the square root of 3 divided by the square root of 4, and the square root of 4 is 2, so the height is √3 divided by 2. But the height of the triangle is adjacent to the 30-degree angle and opposite the 60-degree angle. So the sine of 60 degrees is √3/2, and the cosine of 30 degrees is the same as the sine of 60 degrees, which is √3/2. We can now put those angles into our unit circle. If we consider an isosceles right-angle triangle, we know the two lengths must be the same and the two base angles must be the same. Since the right angle is 90 degrees and all internal angles must sum to 180 degrees, the two identical angles must be 45 degrees. If the hypotenuse is 1 unit and we call the two identical lengths x, then we can use Pythagoras' theorem to get x. So 1 squared is equal to x squared plus x squared, because Pythagoras' theorem says that the square of the hypotenuse is equal to the sum of the squares of the other two sides, and the other two sides are length x. Now a value plus itself is equal to 2 times the value, so 1 squared is equal to 2x squared, because x squared plus x squared is 2x squared. Now 1 squared is 1 times 1, which is 1, so 1 is equal to 2x squared. Dividing both sides by 2, 1/2 is equal to x squared. And again, because we're talking geometry and there are no negative lengths, we're looking at the positive root of 1/2, so x is equal to the square root of 1/2. Now the square root of 1/2 is the square root of 1 divided by the square root of 2, which is √1/√2. And we can rationalise the denominator by multiplying both top and bottom by √2 for simplification. So x is equal to √1 times √2 divided by √2 times √2. But of course √2 times √2 is just the square of √2, which is 2. So x is equal to the square root of 2 divided by 2. So the two lengths, the opposite length and the adjacent length of our right-angled triangle, is just √2/2. But one length is opposite the 45-degree angle and the other length is adjacent to the 45-degree angle. So the cosine of 45 degrees is the same as the sine of 45 degrees, both of which are √2/2. We can now put those values into our unit circle. If we remember that the sine of 180 degrees minus theta is equal to the sine of theta, and the cosine of 180 degrees minus theta is equal to minus the cosine of theta, or the negative cosine of theta, we can extend this unit circle into the second quadrant. For example, the cosine of 120 degrees is equal to the cosine of 180 degrees minus 60 degrees, which is equal to the negative cosine of 60 degrees. If we want to extend into the third quadrant, we can observe that the x-coordinate is the same for 180 degrees plus theta as it is for 180 degrees minus theta. So the cosine of 180 degrees plus theta is equal to the cosine of 180 degrees minus theta. The y-coordinates are as far above the x-axis in 180 degrees minus theta as they are below the x-axis in 180 degrees plus theta. So the sine of 180 degrees plus theta is equal to the negative sine of 180 degrees minus theta. And armed with this information, we can complete the third quadrant of our unit circle. Moving into the fourth quadrant, we can notice that the x-axis values are the same for 360 degrees minus theta as they are for theta. So cosine of 360 degrees minus theta is equal to the cosine of theta. By the way, it's also equal to the cosine of 0 degrees minus theta, or the cosine of minus theta. So the cosine of negative theta is the same as the cosine of 360 degrees minus theta, which is the same as the cosine of theta. We can also notice that the y-coordinates are as far below the x-axis for 360 degrees minus theta as they are above the x-axis for theta. So the sine of 360 degrees minus theta is equal to the negative sine of theta. And armed with this information, we can complete the fourth quadrant. Now, if all this looks a bit overwhelming, it might be a good idea to watch this video several times through until you understand the concepts really clearly. Let me assure you, with a bit of practice, this actually becomes fairly routine and these values become fairly obvious, but it will require a bit of practice and a bit of committing to memory. You will, I'm afraid, be expected to know this stuff for your exam. For example, on a non-calculator paper, you might be expected to know that the sine of 120 degrees is root 3 over 2, or that the cosine of 30 degrees is root 3 over 2. Okay, if this video helped, don't forget to like, comment and subscribe. And I'd like to wish you all the best with your revision and all the best with your exams. And I look forward to seeing you in another video.